SBCJ Engineering, and we're here to present the Portable Intravenous Pump, or PIVP, that we've been able to develop over the past 2 semesters. Before we begin, we'd like to thank our project mentor and client, our mentor being Dr. Hood, and our client being Dr. Jeffrey Evan. They've been a massive help.
My name is Cody Lansford. I'm the project planner and cost analyst.
I'm Brandon Williams. I'm the project team lead.
I'm Sean Palmer. I am the systems analyst.
And I'm James Kelly, the design engineer.
Currently, there are no disposable and portable pumps for rapid infusion. Demonstrated are the usual solutions that the team has set out to outperform. Holding, propping, squeezing, and weighing the saline bag are all methods used by medical personnel as of today. All of these methods provide inconsistent flow rates and leave the operator with one less hand to use during their operation. SBCJ's aim was to create a pocketable tactical vest-fitting IV pump that can work in many rugged environments and high-octane trauma situations.
Intended for trauma infusion, the PIVP can administer saline at a flow rate greater than 240 milliliters per minute. Seen on the right are the 3 syringe gauge sizes that are accounted for in our calculations. The PIVP is able to reach its minimum allowed flow rate through the smallest gauge size. The device is purposed to be disposable as well as to fit with a variety of lure adapters. The inlets and outlets were threaded for this reason. Unfortunately, due to a manufacturing issue, we were not able to receive lure adapters in time for testing. Regardless, the device will induce and sense flow and give an alert if there is any issues with this process. Once alerted, the user can address the stoppage and reset the device by pressing the toggle button twice. Flow will then resume as normal. To ensure the device's base usability, preliminary tests were performed to estimate the battery life at full load, as well as the flow rate from the pump and flow data acquisition from the sensor. Early tests of the device showed that it could push saline through tubing at over 400 milliliters per minute. With the maximum voltage at full load, i.e. system blockage and the buzzers initiated, being 8.5 volts, the device has an estimated runtime of just over half an hour. The system senses these flow stoppages with a sensor that outputs data as a square wave that varies in frequency. When there is no flow, the wave ceases to modulate, which in turn signals the alarm to sound and a reset to be initiated.
Our design efforts were primarily devoted to creating a sturdy housing and arrangement that minimized overall dimensions and safeguarded the internal components. The goal was to decrease the chance for the device to malfunction due to harsh impacts or prolonged vibrations. The interface is very simple due to the client's intent to have this device used on the battlefield and rapid trauma response scenarios. In essence, the user will only have to set it and forget it. We were able to reduce the overall dimensions to 118 by 77 by 58 millimeters. Next, we'll demonstrate the user interface and feedback that is given when the device fails to sense flow.
With full assembly, the PIVP produced a consistent flow rate of 250 milliliters per minute. The device will drain a standard 1 liter IV bag in 4 minutes. It has an easy-to-use interface where the only option is the power switch to turn the device on and off. When low flow is detected, the alarms will sound and the user should turn the device off, reset the line, and turn it back on. During our testing process, the PIVP passed all specified criteria. Out of the 20 tests we performed, some of the most important were for impact fracture, compressive force, high and low temperatures, dirt and dust resistance, and water resistance. Shown here are the shock and drop, dirt and dust, and weight or crushing test results. For the drop test to measure the shell's resistance to impact damage, the PIVP withstood drops onto a hard surface as high as 3 meters. We observed little damage and the device functioned as designed.
Yep, definitely still works. Turn it off. There you go.
To test resistance to continuous stress, the PIVP withstood 60 pounds of force for more than a minute. Our design withstood near freezing temperatures, just below 5 degrees Celsius, for 30 minutes with no effects on functionality. Direct exposure to temperatures above 50 degrees Celsius produced slight deformation but had no effect on performance. After the temperature tests, the device still functioned normally and could detect a lack of flow. The PIVP can resist soil sizes down to about half a millimeter in diameter without significant contamination. Here we see the device fully covered in sand and fully functioning after it is taken out. Also, while fully submerged in depths up to 1 meter, the PIVP will consistently operate. We only observed structural failure after a fall more than double our test height. The device visibly cracked and split, exposing the internal components. Even so, it fully retained the ability to induce flow and to sense a lack thereof. Due to shortages in university printing services, all parts fabricated in-house were printed from PETG. The device was originally designed to be printed from ABS plastic. We expect a more resilient product if made from ABS. In particular, better resistance to heat, impact forces, and prolonged exposure to moisture. As it stands, PETG provided a suitable substitute.
Medical personnel should not have to waste crucial time when dealing with trauma cases. As we've shown, the PIVP will quickly and easily pump saline into a patient within a variety of different environments. Thank you for your time. We'll now open up to questions and comments.